Let us get started. So let us discuss about the control chart types. This is where we have left actually. Depending on the data type, we decide on which chart we have to use. If it is continuous data or variable data, or if it is attribute data, depending on that, we decide the kind of charts that we have to use. Suppose it's a variable chart, and if you know the subgroup size, n is equal to 1 subgroup. If you are taking all the data points from one machine, say Coke bottles are manufactured by one machine, if you take all those Coke bottles and if you plot the height of the liquid within the Coke bottles, it will be IMR chart. If there are 2 to 9 different machines which are manufacturing the Coke bottles, then you use X bar R. If there are greater than 9 machines which manufacture the Coke bottles, then you use X bar S chart. On the other side, if the data is attribute, you ask two things. You ask whether it is defect or defective. If it is defect, and if you know what the subgroup size is, then you go with C chart. If you do not know what the subgroup size is and you know that it is variable, then you go with U chart. And if the attribute data is defective, if you know the subgroup size that it is fixed, you go with NP chart. If it is variable, you go with the P chart. So this is how we decide on which chart we have to actually use. Right? And let us do some exercises. We have few exercises also which are coming up. Things will become very easy. First, let us discuss IMR chart. There are two charts in this. Individual moving range, IMR means individual chart and a moving range chart. It is used when time range for data collection is pretty large or there is one value per subgroup. That means daily there is one Coke bottle that is manufactured by one machine. Daily, it's 24 hours time gap. So there is a huge time gap. So the time range is large. That is when you go with IMR chart. IMR chart has this condition that the data should always be normal. For example, torque is measured daily once in first hour of production and then it is recorded. Then draw a suitable control chart to find if it is in control. Under such circumstances, you go with IMR chart. Let us see whether we can use this example. Let us plot control chart. I'm opening this. Just give me a minute. So while that opens, let me show you here. First thing is we need to check whether the data are normal. Only if the data are normal, you can proceed with IMR chart. So I think it's still coming up. We will plot this, right? But when you plot, it will look like this exactly. This is the same screenshot. And if you see the p-value, it's greater than 0.05. It is 0.066, which is greater than 0.5. 0.05. Hence, you claim that data are normal. Yeah, I think it has opened, yes. So torque, daily once. If you see 7, 1, 2, 3, on a daily basis, we have measured the torque. We have the torque value here. Let me go to, graph. Or I think basic statistics, normality test. There are various ways of finding out the normality. We are going by the traditional way of looking into it. This is a straight line and these are the various torque values, the blue dots. Closer these blue dots are to the line, higher will be the p-value. But if p-value is greater than 0.05, straight away you say that yes, data are normal. Only if data are normal, which is in this case, you proceed with IMR chart. Yeah, so this is how we need to navigate actually. You need to go to Stat, Control Charts, Variable Charts for individuals. Let me go to the worksheet. Stat, Control Charts, Variable Charts for individual, IMR. What is the variable that we want to plot? Torque. Always try to test by enabling all the possible tests that are available. Since this is continuous or variable data, we'll have 8 tests. There are 8 tests here. Let me select all the 8 tests. Clicking on OK. And if at all you want, you can also select that date stamp if you want the date details also in a control chart. This step is optional. It will plot actual dates instead of just integers on the x-axis. So let me go back here. So this is the individual moving range. If you see, there are no red dots here. Only if there are red dots, that means there is an outlier. So there is no outlier in this because there is no red dot absolutely. Okay, but there is another option. Oh, not this one. Okay, you can just select the stamp as date. Let us see what happens if I select the stamp as date. See, instead of data point numbers, we have the actual dates here. That is the only difference. Okay, so the final conclusion is that there are no outliers. Ideally, the control limit should be based on historical performance where we know the process was in control. You can specify the mean and standard deviation here to establish the control limits. All right. What we have done is by default there was one test which was selected. We have removed that and we have selected an option which will ensure that all the tests are performed. Yeah, so this is what we have got. Process is in control because all the points lie within the control limits, that is these red lines. In addition, there is no indication of the 8 out of control tests. There are 8 tests which we have performed. If at all we have any red dots, that means it's violating one of those 8 tests. Here there is no red dot at all, so we can safely conclude that there are no outliers. IMR, in this we have moving range chart also, which is used to assess whether process variation is in control when data has individual measurements. What does it contain? It contains of plotted points for the moving range, which is the absolute value of the difference between two consecutive points. So if I have torque of 6, 7, 8, 9, so on and so forth, moving range says subtract these two, moving range is 1. Subtract these two, moving range is 1. These two, moving range is 1. Suppose I have another data set, 13, 6, 8. In that way, I have a different set of numbers, assume. In this case, you subtract these two, you will have moving range for the first, or you will have the first moving range value. If I subtract, what would be the difference? 4. If I subtract these two, what would be the difference? 7. If I subtract these two, difference would be 2. So these are the moving range numbers. You just subtract two consecutive points. And the absolute difference. What do you mean by absolute difference? If you see here carefully, 6 minus 13 should ideally have been minus 7, right? If I take an absolute value of negative values, it will become positive. Center line green is the average of all the moving range. This green line, this line is the center line, which is green color, which is the average of all moving ranges. Control limits red, which are located above and below the center lines, provide a it provides some arbitrary range which will tell you the amount of variation expected in the moving ranges. Right, for example, these are the red lines that are available. This is the upper control limit UCL, lower control limit LCL. So it's giving you some range within which your process have to perform. Unlike the other charts, there is no possibility of computing within subgroup variation. Why is that so? Because subgroup size is 1. What is a subgroup? Subgroup means if I'm working in shifts, I look into Coke bottles which are manufactured in the morning shift, afternoon shift and night shift. Right? But if I have only one shift, 9 to 6, everyone work from 9 to 6, then the subgroup size will become 1. Subgroup variation is estimated by using between subgroup variation, which we learn. That means if you have machines, 2 machines, 3 machines, etc. Subgroup variation between these two, is estimated by using between subgroup variation. So I'm checking variation between these two. Points that fall outside the control limits are marked in red. Right? And then the IMR chart for the given data has lower and upper limits, which means the moving ranges are expected to fall between these two values. And the center line is 0.241. These values I'm getting from here, 0.2410, 0.870 and all that. None of the individual observations fall outside the control limit. That is what we have seen in the graph also. The points inside the limit display a random pattern. That means you cannot establish a particular pattern. There is no pattern as such, right? It's very random. This graph is really very random. There is no particular trend to it or any particular format. There is no evidence for lack of control. So the moment we look at that graph, it's clear that the process is in control. So the process variation is in control, and it is appropriate to examine the eye chart. Now, in this, we have two things: individual chart and moving range chart. So once we look into the moving range chart, we proceed further to look into individual charts. It assesses whether the process center is in control or not. It consists of the following: plotted points for each individual observation. It contains the green line, which is nothing but the average. It contains the red line, which is nothing but 3 standard deviations above and below the mean. And for the given data, we get these numbers. None of the individual observations fall outside the limits. This is the center line. Hence, we conclude that data is in control. How do we conclude that data is in control? See, there is no red dot here. The moment there is a red dot, that itself is an indication that there is a presence of an outlier. Remember, in variable charts, we perform 8 tests. So there are 8 tests conducted to check for special causes or non-random behavior. Points that fall beyond the control limits are marked in red. Session window should be checked for results, and this moving range chart must be in control for interpreting the individual chart. Else the control limits for the individual chart will be inaccurate. So first look into the moving range chart. Only if it is in control, you proceed to check for individual chart. Okay, so let us look at this example. CC underscore machine. Let me open that. The recording once again. So here is the case study or example that we need to crack now. Exercise is given. Cycle time data for two machines of same utility and different make is given. Find which machine gives controlled output. Which control chart will you use? Okay, so let me go to that particular flow chart. Okay, here is a flow chart. So by looking at this flow chart, can you tell me which chart I have to use? First tell me, is it continuous data or defect or defectives? I'm throwing the values at you. Or you can see this minitab file, machine 1, machine 2. Can you tell continuous? Absolutely correct, continuous. So I'll go back here. It's continuous data, you agree with that. Can you tell me what is a subgroup size? 2. Why 2? Because there are two machines. If there was only one machine from which you were getting the outputs, n would have been 1. So if it's 2, you go with what? X bar R chart. Right, X bar R. So I think let me do that. X bar R chart. Go to stat, control charts, variable chart for subgroups, X bar R. All observations for the chart are in one column. No. Observations for the subgroup are in one row of columns. Yes. Machine 1, machine 2. I'm going to select all the tests. And let's see what will the data show. Okay, here is for machine 1. For machine 1 there is no red dot. That means process is in control. For machine B also, okay. If you see, this is the range. Range also is within control. Mean also is within control. So perfect. But for what did it take? Did it consider both or only one? Okay, so let me go back to the worksheet. Go back to the option. Let us plot separately. Subgroup size is 2 and I want to perform all the tests. So this also for machine 1 it is within control. If you see, machine 1 is within control. So let us do it for machine 2. Machine 2 also, it shows that this is in control. There are no red dots. Oh, hold on. For machine 2 there is an outlier here. Range for a particular value is outside. It's violating which rule? Rule number 1. This number 1 on top of the red dot is telling us that this is an outlier. So now you as a Six Sigma consultant or a process owner should actually investigate on what is the reason for this outlier. This one. So machine 2 there is an outlier. If you go back to my question, the question is find which machine gives controlled output. Machine 1 gives controlled output, not machine 2. Which control chart will you use? X bar R. Can you draw any other conclusions from the result? Yes. We conclude that there is this one outlier in the range chart for machine 2. Okay. So let us discuss more about X bar R chart. Okay. X bar R chart displays two charts. One is X bar chart and one is the R chart. X bar chart is used to determine if the process mean is under control or not. R chart plots the range values, difference between the maximum and minimum of the observed values in sample. R charts are used to determine if the process variation is in control. So look at the difference. Here we are speaking about variation, process variation. In X bar alone, we are looking into mean, variation in mean. X bar R chart is useful to control both mean and variation at the same time. So you look into two things at one go. Here is yet another example. A maker of snack foods has just launched a new dried fruit packaging line. Material usage is shown on is showing an adverse variance for the last month, and Six Sigma team is investigating the source of waste. As a starting point, the data was collected over 20 hours of operation, consisting of 5 observations per hour. Subgroup of 5 observations per hour. The team wanted to assess the behavior of the process, so X bar R charts were created, which are shown below. Shown in subsequent slide. Measurements in ounces per package, which is a target weight of 8 ounces. Okay, so let me open this X bar R. Recording. It has outputs from 5 different machines, for example, right? And here are the numbers 8.7, 8.8, so on and so forth. You have the numbers also available. So why should we use X bar R chart for this? That's the question. Let me go back to this. Okay. Now by looking into this, can you comment on what type of data are we discussing about here in this Minitab file? Is this continuous data or discrete data? Continuous data. How many subgroup? What is the subgroup size? 5. So if it's continuous data and if n value is in between 2 to 9, which is 5 in our case, we go ahead with X bar R chart. Okay, so that is why we are using X bar R now. We are going to use X bar R. So let me take you to that particular slide. Okay, so go to stat, control charts, variable charts for subgroups. Stat, where control charts, variable size for subgroups. Here we are going ahead with X bar R. All observations of a chart are in one column. No. Observations of the subgroup are in one row of columns. I select everything 1 to 5. X bar R. Once again, let us look for all the tests. When we look into all the tests, then truly if we do not have any outlier, there won't be any red line. So that's it. Okay and okay. It's going to show us a chart. Here it is. Yeah, so by looking at the chart, can you comment on it? Is there any outlier here? So process is stable. The final statement that you as a statistician will make will be as simple as this. You will say that there are no outliers, hence process is stable in statistical terms. So here also look at this statement. Ideally, the control limit should be based on historical performance, where we know the process was in control. Earlier, when process was in control, right, you would have collected some data. Based on that data, you will have to come up with the mean and standard deviation. Those values you put here, mean, standard deviation, which will help you calculate your control limits. Otherwise, these control limits are calculated based on some formula which we are going to discuss. All right. So let us see what our analysis has to say. The process is stable, no out of control conditions, but the mean is 8.6, which is well above the 8 ONS target with a fair amount of variability. It appears that this process requires further scrutiny. Yes, we are telling that it has to be 8 ounces. That was our target. But if you see, the mean is 8.6 here. 8.6. It appears that this process requires further scrutiny. Yes, it requires further scrutiny. We use the X bar R chart to check whether the process center is in control or not. What does it contain? It contains the plotted points. These blue dots are the plotted points. It also contains the green line, which is a center, which is nothing but the estimate of the process average. It is the average of all subgroup average. Right, this green line is an average. Hence you see X bar bar. X bar itself means it's an average. Average of average will be shown as X bar bar. Yeah, so whenever you see this kind of notation, X bar bar, you need not be surprised. That means we have taken average of already averages. There are 5 subgroups, 1, 2, 3, 4, 5, right? Let me show you that. There are 5 subgroups, 1, 2, 3, 4, 5. If you take average of these numbers, average of these numbers, average of these numbers, average of this 4, average of 5. Once again, if you take average of those averages, it will become X bar bar. That is what is mentioned here. The red lines which you see here are the control limits. Control limits represent the amount of variation which is expected for the subgroup averages. All right. Yeah, that is pretty much that is explained here. Points that fall outside are marked with a red symbol and the number of the failed test. So on top of it, you will see a number 1, 2, 3 until 8. Question to you, Anuj. Why do you see numbers from 1 to 8 only on those red marks which are outliers? Why not 9, 10, etc.? Okay, don't know. Let me show you that. Here, this is an outlier, right? There is a number 1 which is mentioned here. Why 1? I'm telling it can be only till 1 to 8. Why not beyond 8, 9, 10, etc.? Because there are only 8 tests. Either it will violate test 1, test 2, test 3, 4, 5, 6, 7 or 8. So, if you see here, how many tests do we have? If you count them, you'll get 8. So there are only 8 tests, hence the number cannot be beyond 8. All right. So R chart must be in control before X bar chart is interpreted. If the R chart is not in control, then the control limits for the chart will be inaccurate and may inappropriately signal an out of control condition on the chart. For the given data, The R chart is in control, right? When we have actually plotted and checked, it was in control. If the R chart was in control, then we went ahead and looked into X bar also. UCL, LCL and the average can be seen from the graph. If it's not in control, identify and correct the contributing factors. R chart. Assess whether the process variation is in control or not. It's not the mean now, right? X bar chart, see in X bar R chart, X bar is used to check whether the mean of the process is in control or not. The moment we discuss about range, we discuss about the variation. It consists of plotted points for subgroup ranges. There will be, we can stop after this. It consists of plotted points. Yes. It consists of a green line and a red line. Green line is the average and the red line describes the amount of variation. A failed point is marked in red, which indicates that there is a non-random pattern, special cause variation. In the given data, none of the subgroup ranges are outside the control limits. The points inside the limits display a random pattern. There is no lack of control in variation. It is appropriate to examine the chart to determine whether or not the process center is in control. So all these statements that I'm making those statements by looking into the simple plot, X bar R plot. If you see this range chart is also within the limit. This mean also, that is X bar chart also is within limits. So X bar R both are in control. Hence we conclude that our entire process is stable.